All right, so here's another example to go with. In this particular case, we're going to do left-hand Riemann sums. And I already have all of it worked out for us, and a few extra pieces that I'll explain here in a second as well. So we have the function 2x plus 1. We're going to do 4 subintervals of this function, and that means that we have the beginning of the interval at 1 and the end of the interval at 3, because that's the way I have this lined up. I even marked the upper points there. Left-hand Riemann sums. This is that generic formula that we're going to use anytime we need to use left-hand Riemann sums, which is the beginning of the interval minus the end of the interval minus the beginning of the interval, divided by the number of subintervals, times the summation from k equal 1 to n of the function evaluated at the beginning of the interval plus the width of each rectangle times k minus 1. All right, so the first one we do is we figure out our width, which was 3 minus 1 over 4, which is 1/2. I mean, it's 3 minus 1 because that's the end of the interval minus the beginning of the interval, right? Which is 3 minus 1. And then the number of subintervals is 4, so that's 1/2 there. And then we got that plugged in. So the summation just simply means start at this value right here, which in this case is 1, and go up to that value right there, which is in this case is 4. So we're just going to plug in 1, 2, 3, 4 independently of each other into k, and that's going to give us 1 minus 1, which is 0, times 1/2, which is 0, plus 1, which is 1. There's our first value. We're going to plug in 2. When we plug in 2, we get 2 minus 1, which is 2 times 1/2, which 2 minus 1, which is 1, times 1, which times 1/2, which gives us 1/2, plus 1, which gives us 1.5. Plug in 3, you get 2. You plug in 4, you get 2.5. I'll let you kind of run through some of that on your own. You can pause at this point and just kind of verify that for yourself. Then we take these values and we plug them into the function. So you plug in 1 into the function, so 2 times 1 plus 1. You plug in 1.5. 1.5 times 2 plus 1 gives you 4. You plug in 2. 2 times 2 plus 1 gives you 5. And then the last one, you plug in 2.5 times 2 plus 1 gives us 6. 3 plus 4 plus 5 plus 6 gives us 18. 18 times 1/2 gives us 9. So we know that there is approximately 9 units under there. And keep in mind, this is approximate. This right here I have equals because this is actually the left-hand Riemann sum here. But this is approximately the sum, the integration from 1 to 3. Okay? This is not the exact summation from 1 to 3. This is the approximate value there. So it's not going to be the exact area. Now, what's interesting about this particular one, since it have a straight line, is we actually have a really solid trapezoid there with a base of 3 and a base of 7 and a height of 2. Right? So the span here is 2 from 1 to 3. The span right here from the x-axis to up here is 3. This is also 7. And when we do that, formula for a trapezoid is base 1 plus base 2 times the height times 1/2. So that's 3 plus 7, which is 10, times 1/2 times 2, which is 10 units squared. So 10 units squared would be the exact value, and 9 is what we came up with when we did the approximation, which is a pretty solidly good approximation. Now, that's not saying that we can't do better than that. We obviously can. Now, the idea here is, how would we do better? How would we get a better approximation? How do we get it closer to 9? Okay, so what does that next stage look like? Well, what we would do, okay, we could take the exact same function. Looks like this. We're still dealing with 2x plus 1, right? And in this case, what happens when we let n equal to, say, 20? Now, doing this by hand gets really messy, but you're still doing the exact same process. It just takes more steps. So you have 3 minus 1 over 20, which gives us 1/10 is the width, which means that we break this down from 1 to 3 here. We're talking about creating 10 intervals inside of here, right? And in this case, each of those is going to be smaller than it was before. So theoretically, the amount of little gap here that we would have, that error that we would have right there that we're not actually being able to count, is going to get smaller and smaller and smaller every single time. And that's when n equals 20. But what happens when we let n go off to 100? Or what about if we let n go off to 1,000? Now we're starting to talk about the idea of a limit. So if we say the limit as n goes to infinity of this summation, and I forgot my w piece here, we'll just say w times the summation from k equal 1 to n of f of a plus b minus a over n, and then k minus 1, because we can deal with the left-hand sum here. This would be exactly the integration from a to b of f of x dx, right? Which is pretty cool. And we're going to deal with this more here in a little bit. The short of it is that we would just simply do the integration from 1 to 3 of 2x plus 1 dx, right? And if you remember integration from Cal 1, that would just simply mean that we have x squared plus x evaluated from 1 to 3. I don't know if you remember this. If you don't, that's okay. We will review this in detail later on. And in that case, we end up with 3 squared plus 1, which is 10, right? No, I'm sorry. Scratch that. I did that wrong. A 10 is hang on. So we have 3 squared plus 3 minus 3 plus 1, like that. There we go. So that's a 1 there. Oh my goodness gracious. So anyway, we end up with that, which ends up giving us 3 squared, which is 9, plus 3 minus 2, which gives us 9 plus 1, which is 10. Like I said, 10 is the correct answer. I just did it wrong, but oh well, we got it right now. And if you remember, when we did the exact area for that with the trapezoid, we found it to be 10, and there it is, 10. Now, you can repeat this process, and I encourage you to do that. Repeat this process with a larger value of n. You don't necessarily have to do 20, but you could do 10. You could do 5, you could do 6. And what you're going to find is that this value is going to get closer and closer to being 10. You could also come back through, and instead of doing the right-hand Riemann sums, you could just switch this to just being k, in which case you're doing the, instead of doing the left-hand Riemann sums, you could do the right-hand Riemann sums, and see what that does for your value. And we're going to look at all those examples as we go through this and do more of them. And then there's also some other stuff that we can do with summations as well. All right, thank you.